good, yeah.
Oh, um, sorry, Professor, we have a delay. 30 minutes, yes, but maybe we can check now the connection, if you want.
Yeah, sure, yes, yeah, well, let me try that. So, let's see if I can share. So let me just bring up. There we go. Can you see that?
Yes, I can.
Good.
Everything is okay.
Right. In fact, let me just see if actually I should go to full screen. Does it?
Yes, I can see the slides and you also.
Good.
I think the people is coming. I think 5 minutes more.
Yeah, sure, no problem.
Okay. Okay. Professor, please wait me some couple of minutes, please.
Yeah,
Okay, yeah.
sure.
empezar, ¿no? Hello, we are going to start. Professor, can you hear me?
Yes, I can hear you loud and clear. Hope you hear me okay?
Yes, Professor. I'm so sorry, Professor, but we are going to start now.
Yeah, that's fine.
Yes. Good. Professor David Wans is the next speaker. Yes. Professor David Wans is professor from the Portsmouth University. Yes. And then, so sorry, Professor, but you have the word now.
Okay, thank you. Can you see my screen okay?
Yes, we can.
Good. Okay, so in fact, I took a photograph from my window an hour ago. So this is my I'm in Portsmouth in my office in the university with a nice evening sunset. Now, now it's just dark. It's night here. It's a shame I can't be with you in person, but it's a very busy time of year. It's the start of our academic year, so I have a busy few weeks teaching the undergraduate students here. But I'm glad I can be able to join you virtually and tell you a bit about my some of my research interests at present, and in fact over a number of years studying inflation in the very early universe. And so today I was going to mainly probably review some results on what I called adiabatic and non-adiabatic aspects of inflation. So there's a few papers I've been working on this recently. One in particular at the end of last year with our student Joe Jackson and colleagues in Portsmouth and Paris. So some of the results I present will be from that. But we've also got a new paper coming out on the archive, actually just submitted this afternoon. So I'm not sure to look out for that tomorrow on the archive. And indeed, another paper in preparation with a strong South American connection, Argentinian and Brazilian input, work with Danilo Artigas, Manu Frion, Tesh Miranda, Vincent Venin, also in preparation. That may be a week or two away. So I should start maybe by giving a bit of historical context. Well, I'm going to start with why I'm interested in inflation, really because it provides a physical model to understand the origin of structure in our universe. So inflation provides the initial conditions for the generally successful lambda CDM model of cosmology. And in particular, it produces can produce a spatially flat Robertson-Walker background. It can produce a large smooth universe through the classical expansion of space-time. But crucially, it also provides a model for the origin of density fluctuations, and therefore we think of all structure in the universe, in the late-time universe that we can observe today. So it's worth sort of taking a historical sort of viewpoint as to how how inflation has survived as an idea since the 1980s, even with all the new cosmological data that's come in that time. When I started as a PhD student in the early 1990s, there was, especially in England, a lot of work on one particular elegant, simple, and well-motivated model for the origin of structure in our universe. And that model was topological defects. That's objects like cosmic strings that could form in the early universe through spontaneous symmetry breaking. And this seemed to have was investigated by people like Tom Kibble and many others especially in England. And it seemed very natural result of spontaneous symmetry breaking in ground unified theories. It was a beautiful explanation for the origin of structure in the universe through this spontaneous breaking of symmetry. and it could be tested by observations. So predictions like this sort of curve here, shown in the late 1990s, by the early 1990s, this was perfectly compatible with the little information that we had about large-scale structure and the cosmic microwave background, anisotropies in particular. Even by the late 1990s, the data was beginning to show evidence of more structure in the cosmic microwave background angular power spectrum than topological defects could provide. And ultimately, in the 2000s, this model just doesn't work as a model for the origin of structure. Instead, what we have are these fantastic observations, such as the data shown here from the Planck satellite, the 2018 data, where you see, in fact, not just the temperature power spectrum, but also the polarization power spectrum and cross correlations. And inflation predicts, or at least can explain, the detailed structure that you see in the angular power spectrum. The predictions of inflation naturally give rise to an almost scale invariant spectrum of primordial perturbations, to the first approximation Gaussian, and for the purposes of this talk, crucially, they're adiabatic density perturbations. So, and that provides this fit to the data that's come in over the recent years. The only tantalizing thing is that if we could really see a spectrum of primordial gravitational waves consistent with these models of inflation, then that would be a really distinctive prediction for inflation that could yet be tested by, in particular, the cosmic microwave background radiation. So inflation has survived the sort of, the era of precision cosmology. I would argue that, in fact, the simple models of inflation have been very successful. But it's worth testing and thinking about some of the assumptions behind that model, in particular, the notion of adiabatic perturbations produced from inflation, and the possibility that we could test deviations from that, especially on scales that are not so well studied, not so well constrained by the classic observational constraints such as the cosmic microwave background. So that's what I'm going to talk about a bit today. I'm going to talk about that in the context of single field inflation. So inflation can be driven by a single scalar field. I'll label this phi of t throughout. And that can drive the expansion of the universe. And indeed, the Hubble expansion, even with or without inflation, our standard Friedmann-Robertson-Walker space-time, the Hubble expansion corresponds to an adiabatic expansion, adiabatic in the sense that there's no heat transfer, there's no exterior, nothing outside the universe. So the density evolves just due to the local expansion. And in inflation, the simplest case of single field slow roll inflation, we're interested in a single scalar field with a potential energy, a self-interaction energy density. And so the potential and kinetic energy of the field drives the Hubble expansion through the Friedmann equation, and the Hubble expansion in turn damps the evolution of the field as it evolves, as it would accelerate down the potential driven by the potential gradient. But as well as this driving term from the potential gradient, there's a damping term due to the Hubble damping. And if that slows the evolution of the field sufficiently so that the potential energy dominates over the kinetic energy, then we have the condition for inflation, which I will define to be an accelerated expansion in the very early universe. And this turns out to be crucial not just in driving the universe. The Robertson-Walker metric, for instance, is driven towards a spatially flat geometry. isotropizes the universe, can homogenize the universe classically, but also if we start considering quantum fluctuations of the field driving inflation, it's this accelerated expansion that can connect small-scale quantum fluctuations with the large-scale structure of our universe. So the idea here is that even if you wanted the universe to be perfectly smooth and perfectly homogeneous, it's just not possible in a quantum mechanical world. The fields driving inflation inevitably have inherent quantum fluctuations. And on small scales, in fact, scales smaller than the Hubble length associated with the expansion of the universe, these quantum fluctuations are just the free, underdamped oscillations of a quantum field. So they can be quantized and studied using techniques of perturbative quantum field theory in a expanding background geometry. And inflation, though, it's the condition for accelerated expansion is precisely the condition for co-moving modes being stretched by that expansion to cross beyond the Hubble scale, because the Hubble length stays constant or at least slowly varying during inflation, whereas the rapid expansion of the scale factor stretches the wavelengths of these modes up from, so what I'm going to call the sort of ultraviolet regime on sub-Hubble scales, wavelengths smaller than the Hubble length, into the infrared regime, the long wavelength regime, where the wavelength is much longer than the Hubble scale. And this same Hubble expansion, as I was mentioned, has a damping effect on the evolution of the scalar fields. And that actually drives these what are inherently quantum fluctuations, but it drives them into a squeezed state. So that although it is truly fundamentally a quantum fluctuations, they can effectively be described by a classical random field in the large scale limit in which we have this squeezed state. And so actually in this large scale limit, we use classical dynamics of the field typically, and we also use this long wavelength approximation to study the dynamics in the limit in which the spatial gradients can be neglected. And that means that in each Hubble patch, in a sort of typical Hubble length, or indeed even on larger scales, the evolution can be modeled as effectively like separate universe is different patches of the universe can evolve independently as separate universes. And then we can use the nonlinear equations of the Friedmann-Robertson-Walker cosmological expansion to actually give a fully non-perturbative description of the fluctuations if they're in this long wavelength regime. And that's the basis of approaches to studying sort of nonlinear fluctuations, non-perturbative fluctuations. I'll mention briefly the sort of delta N approach. It's also the stochastic studies of inflationary dynamics are done in this separate universe approximation. So that's inherent in the nature of inflation, this link between quantum fluctuations on small scales and then the large scale dynamics in this separate universe regime. So as I say, the separate universe assumption is that we're basically going to think of the perturbed universe on large scales as basically being composed of patches that evolve like effectively separate universes. And I mean, at some level, this is sort of inherent, even in the way we think of our observable universe. I don't suppose that the universe on unobservably large scales is necessarily even close to the local behavior in the part of the universe where we live. But what we do observe is approximate homogeneity and isotropy in our observable universe on looking at the cosmic microwave background sky. So it seems a reasonable assumption to model the evolution of our observable universe using this the homogeneous and isotropic Friedmann, Lemaitre, Robertson, Walker space-time. And just as we do that in our observable universe today, effectively on the Hubble scale today, then this is what we're doing in the separate universe approach, even at much earlier times in the universe, because the Hubble scale, the characteristic scale of expansion was much smaller then. So even on what are now smaller scales, it can, especially during inflation, once waves have been stretched into the super Hubble regime, it can be a very good approximation to drop spatial gradients and anisotropies. And this sort of approach was pioneered by Salopek and Bond in a classic paper in 1990, where they sort of developed this gradient expansion. And what we're talking about here is taking the zeroth order, where you expand the inhomogeneous universe in terms of the spatial gradients. But basically, we drop the spatial gradients at zeroth order. So I'll come back to that, and that's an important simplification, I think, for understanding the fluctuations we produce from inflation. But also, we have to be careful as we go beyond the simplest models of inflation as to whether these assumptions are still valid. But as I say, in this picture, that's the context in which we understand the fluctuations that we see on the cosmic microwave background sky here. The origin of what we see as fluctuations in the density in the primordial plasma, a sort of plasma of photons, baryons, and electrons tightly coupled before last scattering. We see inherent density fluctuations, and we understand those as arising from inherently statistical quantum fluctuations, which start actually in a vacuum state. Indeed, the sort of typical thing is we assume they started in the Bunch-Davies vacuum state, which itself we refer to as an adiabatic vacuum state, in that it starts with no particles, and the expansion is slow enough in a sense that the particle number doesn't change with the expansion of the universe. And that then seeds what, in a different sense, are termed adiabatic density perturbations in the photon baryon plasma. So you can see I'm going to use this dimensionless quantity R to characterize the fluctuations both from inflation in terms of sort of the field fluctuations delta phi, and we can map that, in the simplest cases, we map that directly onto the density fluctuations in the primordial plasma. And the reason we can do that is R is a geometrical curvature perturbation, which is inherited for these simple models of adiabatic density perturbations. It's the curvature perturbation in the primordial plasma is directly related to the field fluctuations, the curvature perturbation generated from field fluctuations during inflation. And that curvature perturbation, for example, on large scales, we can simply relate to the temperature fluctuations in the cosmic microwave background sky. It's kind of simply related to the Newtonian potential as well. But what we're seeing on the sky are basically these curvature fluctuations on the large scales, with more complicated physics happening on smaller scales, where the plasma physics begins to play a role. Okay, so these are, but it's important that to fit the observations, we need these adiabatic density perturbations on the large scales probed by the cosmic microwave background. And they're adiabatic in this specific sense. The way adiabatic is used in cosmological perturbation theory is to say that the fluctuations, delta rho in the density, for example, and in the pressure are related in this very specific way. So if we look at the photon baryon phase space. For example, we plot the pressure on the y-axis against the density on the x-axis. The pressure, of course, just comes from the photons, but an adiabatic density perturbation means that local patches of the universe, the fluctuations in the density, are such that and pressure are equivalent to fluctuations along the background trajectory in the phase space. So the background universe is evolving from high density and pressure down to low density and pressure. And for adiabatic fluctuations, the fluctuations in density and pressure, or equivalently the fluctuations in the baryon photon fluid, are they're fluctuations along that background trajectory. In particular, the photon to baryon ratio remains unperturbed along this trajectory. But if you had fluctuations in the relative photon to baryon number, then that would be a non-adiabatic fluctuation. But the evidence we see for the primordial perturbations is that they are actually purely adiabatic fluctuations on large scales. You notice that I'm using the sort of background, the phase space trajectory of the Friedman, Lemaitre, Robertson, Walker cosmology, the homogeneous and isotropic background, to describe actually the fluctuations, so inhomogeneities in the universe. But again, that kind of makes that's a useful thing to do in this super Hubble large scale limit, where again we're working this sort of separate universe picture where the fluctuations correspond to perturbations in the homogeneous and isotropic phase space. Okay. So any non-adiabatic perturbation that would affect, these are also called, in terms of the primordial plasma, we'd call them isocurvature or entropy fluctuations. But the evidence so far in the cosmic microwave background is that we just have adiabatic density fluctuations. And so to understand why we get that from models of inflation, we should actually look at the phase space. So this is the phase space for the photon baryon plasma, the primordial plasma. But if we go back to the scalar field, we can think about the phase space for the scalar field evolving in the expanding universe. And remember, there's this second order differential equation for the evolution of the scalar field. The acceleration being driven by the potential gradient and damped by the Hubble damping. So in principle, you can have, you've got a two-dimensional phase space, basically. The phi and phi dot can vary independently, and then the equation of motion tells you about the acceleration phi double dot. And most models of inflation traditionally have studied this slow roll regime in the phase space, which is where the Hubble damping is large, and there's a quasi-equilibrium solution where the damping effectively balances is both in equilibrium with the potential gradient. So the acceleration of the field is very small. In effect, therefore, then the velocity actually becomes effectively a function of the scalar field, because it's just balanced. It's the potential gradient divided by the Hubble damping. So we have a solution phi dot of phi, this slow roll solution, and crucially, it's an attractor. So if we look at the phase space for a simple inflation model like say a quadratic potential energy for the scalar field, you get this sort of typical phase space for phi on the x-axis and phi dot on the y-axis. For large field values, you see the evolution rapidly approaches this attractor solution, which is a slow roll solution. Phi dot is small relative to the potential energy. And so we naturally only get adiabatic solutions because even if the quantum fluctuations fluctuate about this slow roll trajectory, the damping rapidly drives them as they move into the large scale regime. They're also driven into this along this attractor solution. So effectively, we only have a one-dimensional phase space, and so we can only have adiabatic density perturbations. So the fluctuations then are characterized by simply an evolution forwards or backwards along this trajectory. If we actually look at in linear perturbation theory, the evolution equation for this dimensionless perturbation R, we get as we'd expect, a second order equation for the fluctuations in the curvature. And in this long wavelength limit that I keep referring back to, this is the limit in which we drop the spatial gradients, this final term here, then you can see that we have a simple sort of solution for the evolution of the long wavelength curvature perturbation. There is this constant, there's a constant solution, R primed can be 0, that's a valid solution. And then there's a solution which goes as the integral of 1 over z squared. Z's this variable, but in a slow roll solution, phi dot and h change slowly, so z is basically growing with the scale factor of the universe, and this is a sort of rapidly decaying term. So the co-moving curvature perturbation goes to a constant on large scales. That's why it's we can map that. We can map the curvature perturbation R from inflation onto the density perturbations in the primordial plasma, or even in the distribution of galaxies at late times on very large scales, because the decaying mode rapidly disappears during slow roll inflation, and we're just left with this constant adiabatic solution. So in fact, the amplitude of that set by the quantum fluctuations. So this quantity can sort of easily has a sort of simple interpretation in as the perturbation in the logarithmic expansion in different patches of the universe. So the field fluctuation causes a fluctuation in the expansion. You can think of this, therefore, this perturbed expansion as basically delta n here, as being h times the time fluctuation delta phi of a phi dot, the fluctuation along the trajectory. And that perturbation in the expansion gives the curvature perturbation, the geometry. And as we've just seen, there's a solution where that's constant on large scales. That's the adiabatic solution where it's constant on large scales. So the power spectrum, for example, for the dimensionless curvature perturbation related to the density perturbations is just related by h over phi dot squared to the power spectrum for the field fluctuations. And if we know what the quantum fluctuations in this simple case are doing as modes cross outside the horizon, then this quantity then remains constant on large scales. And because these quantities h and phi dot are slowly varying in slow roll inflation, this is naturally a sort of scale invariant spectrum for the curvature perturbations. And although I won't talk about sort of show the nonlinear evolution of the curvature perturbation in this talk, in fact, this identification of the curvature perturbation with the perturbed expansion is a nice way one way to understand the nonlinear curvature perturbation that can be produced from field fluctuations simply as a nonlinear dependence of the expansion in different patches of the universe, and how it non-linearly depends on the field fluctuations. So even if you have Gaussian free field fluctuations, this can give rise to a non-perturbative, non-Gaussianity in the curvature geometrical perturbation produced from inflation. Okay, so I think I've spent half my talk time talking, well, probably more than half, talking about the standard adiabatic evolution of the universe. So let me, having set all of that up, talk about how in recent years people have become interested in breaking some of those assumptions. And if I come back to the sort of discussion of the phase space for scalar fields in inflation, you'll notice on my slide, as well as this sort of quasi-equilibrium regime, which is the well-known slow roll behavior, there's also this alternative regime that's been studied recently called the ultra-slow roll regime, which is a regime where really you're looking at the free evolution of the kinetic energy of the field, where the driving term here, the potential gradient, is small. So this is very generic in the sense it doesn't depend what the details of the potential are, as long as the potential gradient is small compared to the damping term, then you get this free evolution of the field. It tends to be, because of this damping term, because it's a damping term, this tends to be a sort of transient decaying solution. So it tends to be a short-lived phase in the evolution of the universe. So it's not scale invariant. It doesn't, we don't expect it necessarily to produce structure across a wide range of scales, but we might see features from this type of evolution if we can generate this ultra-slow roll phase during inflation. And that's exactly what happens in models which, and people study these models because they're interested in producing large enhancements in the density perturbations on small scales during inflation, perhaps during the late stages of inflation. And if you look at the form that I wrote down for the primordial power spectrum, you can see that one way to enhance the curvature perturbation would be to have a large increase in this prefactor in the way that the field fluctuations are related to the curvature perturbation. So there's this prefactor h over phi dot. So if you can make phi dot very small compared to h, or can decrease phi dot rapidly, then this would drive an enhancement in the primordial power spectrum. So you might expect you naturally do that by making just a very flat part of the potential. And if you have a region of the potential where the potential gradient becomes very flat, that's exactly the ultra slow roll regime that we were talking about. Power spectrum that people are interested in here is a model of inflation which does have a almost scale invariant adiabatic fluctuations on the large cosmic scales seen in the cosmic microwave background, but which on much smaller scales you could have a large enhancement produced by this sudden transition to an ultra slow roll phase. And that means there could be sort of a whole new range of phenomenology in models of inflation, which are not directly tested by the cosmic microwave background, but could give rise to other observable effects. So very large density perturbations, well, they will generate gravitational waves at second order. If you've got large density perturbations, these are large pressure waves crashing around in the early universe, they will generate secondary gravitational waves. So this can give rise to a stochastic background of gravitational waves. And more speculatively, perhaps, if the amplitude of the fluctuations are large enough, they could collapse in some regions to form primordial black holes. And this is an idea that goes right back to Bernard Carr and Stephen Hawking in the 1970s, to considering whether you could form black holes on a range of scales in the early universe. And if the Hubble scale is very small at early times in the universe, these could be small black holes, small enough even to evaporate by the present day, or perhaps to be some contribution to the dark matter today. So there's a whole sort of industry of people studying these kind of models for these reasons. And in particular, of course, if you could see both evidence for primordial black holes and second order induced gravitational waves, then that would be strong evidence for these large density fluctuations from models of inflation. But to do this, you have to leave the slow roll regime. You basically can't do this in slow roll inflation. And that means that the phase space looks a bit different. These models start in slow roll at early times, and they would return to slow roll naturally after this transient ultra slow roll phase. So you have the attractor before and after this phase, but then this sudden transition into ultra slow roll means that you move into a regime where uh, either there isn't an attractor solution, or indeed our universe, the background solution, does not actually follow the local attractor solution anymore for this period. It basically has to relax back down onto the new attractor solution. And that means you've got the possibility for independent fluctuations in phi and phi dot. And these are non-adiabatic fluctuations. And what you see in these models, as we actually studied way back in 2001 with Sam Leach, Misao Sasaki, and Andrew Little, that can give an enhancement. Means that these non-adiabatic behavior during ultra slow roll can enhance the curvature perturbation R here on super Hubble scales. So this graph is trying to show the power spectrum. And now you can plot the power spectrum for the curvature perturbation as modes leave the Hubble scale during inflation. That's actually this red curve here. And compare that with actually the final amplitude of the curvature perturbation at the end of inflation. And you find that for the modes at the peak and the modes drive the rapid rise in the power spectrum, these are actually being enhanced on super Hubble scales. So they keep evolving outside after the modes have left the horizon because of the non-adiabatic, albeit transient behavior, and then it settles back down into the final attractor solution. So this is a sort of transient non-adiabatic behavior. If you study the mode equation here, you can kind of understand this. This is the Sasaki-Mukhanov, for the experts, this is the Sasaki-Mukhanov mode equation. And the effective mass term here in these models is slowly varying in the slow roll phases, but then there's a sudden feature which kicks the solution from slow roll into ultra slow roll. But that sudden transition is non-adiabatic in the sense that it kicks the fluctuations out of the adiabatic vacuum state on small scales. So you have particle production, non-adiabatic behavior in the quantum field on sub-Hubble scales, but you also have non-adiabatic perturbations in the cosmological sense on super Hubble scales. So we have to follow the evolution of both the non-adiabatic fluctuations on the large scale. So coming back to the evolution of the curvature perturbation in single field, we had this solution for the sort of long wavelength limit of the curvature perturbation. We had this constant mode that was the adiabatic fluctuation on large scales. And what's happening now in these models is what we thought was a decaying mode in slow roll, because phi dot and h were slowly varying. Well, in ultra slow roll, actually phi dot is rapidly varying, and in fact it's varying proportional to a to the -3. So actually z is not increasing with the expansion of the universe, it's decreasing with the expansion of the universe. And so what you thought was a decaying term can start growing. So we have to, and although it's a transient phase, you have to follow through that model, that evolution, to correctly predict fluctuations at the end of inflation. And that's a little bit of, it goes against the common folklore for how fluctuations from inflation should behave on large scales. In fact, very generally in single field inflation, you can write down a general result for the time derivative of the curvature perturbation and relate it directly to the non-adiabatic pressure perturbation, where in the, say in general and in the large scale limit, the pressure and density of a scalar field can vary independently, because if phi and phi dot vary independently. So it would be zero, the non-adiabatic part of the pressure would be zero if the pressure is a unique function of the density, or if phi is a function of, phi dot is a function of phi, as in slow roll. But in ultra slow roll, that's simply not the case. There isn't an attractor solution. So we need to keep track of the non-adiabatic pressure in ultra slow roll. But in the work of Salopek and Bonds, they noticed that the time derivative of R is proportional to spatial gradients of the Bardeen potential. And so they used that to argue that when studying field fluctuations in slow roll inflation, they necessarily became adiabatic, because you would expect spatial gradients of the Bardeen potential to vanish. But what we're seeing in ultra slow roll is models, that's simply not the case in general. And so to actually study the super-Hubble dynamics, you have to include non-adiabatic pressure perturbations. So in fact, you have to include a finite contribution from spatial gradients of the Bardeen potential, which is, and many works actually work in a large-scale limit in which because they're working with the Bardeen potential, they force the non-adiabatic pressure to go to zero in this large-scale limit. But that's not just a gauge choice, that's actually a physical restriction on your model. So this is what we've been studying with Danilo Artigas. I think the solution is to study these fluctuations in a gauge in where you can have non-adiabatic pressure perturbation in the large scale limit. And that is, for example, the spatially flat gauge, which is the gauge in which the Sasaki-Mukhanov variable, commonly used, is defined. So it's fine to study the fluctuations in the Sasaki-Mukhanov variable in the long wavelength limit, but you should be wary of enforcing constraints from the behavior of the Bardeen potential in the long wavelength limit. So it's a technicality for those of us interested in studying the long wavelength perturbations in different gauges. More generally then, so one can ask whether the separate universe approach is valid in these ultra slow roll models. And so I think if you use the spatially flat gauge, it's fine to study either ultra slow roll or slow roll in this at zeroth order in the gradient expansion in this separate universe approach. But one thing we do see is that if you try to model the long wavelength behavior, so here I'm looking at the evolution of a mode, so the curvature perturbation with time for a mode that leaves the Hubble exit before this sudden transition from slow roll to slow roll. So if you try to model it in terms of the long wavelength limit before the transition, it settles down, as you expect in slow roll, into a constant adiabatic solution. But actually, it stays that way after the transition, and if you strictly stick to the long wavelength limit. Whereas actually what the true solution does, the true inhomogeneous solution, is this blue mode, which actually changes dramatically after the transition. And what we're showing here in this rather complicated graph is showing that we can model that through another long wavelength limit. This purple long wavelength limit does in fact correctly describe the separate universe behavior after the transition. So we have a zeroth order in the gradient expansion behavior that describes the evolution before the transition in orange, and after the transition in the purple. But actually they're not the same solution. There's a discontinuity between them at the transition. So this sort of long wavelength approximation works in slow roll, it works in ultra slow roll, but actually it breaks down at the non-adiabatic transition between the two. So this long wavelength limit we use, called the separate universes approach, really only applies piecewise before the transition and after the transition. So I'm sort of beginning to go into the details of how we model the fluctuations here. The significance of this is that remember, the separate universes we want to use for studying non-perturbative or the non-linear evolution of the fields. So in the linear theory, there's no ambiguity really. We can solve the full mode equation. But to go into the non-linear evolution of large fluctuations that could be forming primordial black holes, for example, we want to study the non-linear evolution. And so that's challenging in these models with sudden transitions. It's not that we can do it in slow roll, we can do it in ultra slow roll, but we have to include the spatial gradient terms at the transition between the two. So I hope that's conveyed some of the sort of issues that I've been interested in working on in recently in studying these models of inflation beyond the standard models. I was just going to wind up, and I'm hopefully got time for some questions if people have questions about this. First of all, I would emphasize that simple models of inflation do remarkably well. Single field slow roll inflation remain consistent with observations, and just it's worth bearing in mind that it didn't have to be that way. These inflationary predictions were out there before we had the really detailed observations of the cosmic microwave background. So for large scales, such as the cosmic microwave background, they still do remarkably well. But we're interested in, we're limited information. It's so successful that actually it actually produces a fairly simple power spectrum on large scale with relatively limited information. So we're very interested in finding out more information if we dig deeper into the phenomenology of inflation. Perhaps there's more information in the cosmic microwave background, especially if we can find evidence for gravitational waves on large scales. Galaxy surveys are getting better and better at probing the primordial fluctuations that give rise to large-scale structure. And it's possible that there could be a stochastic background of gravitational waves, which there's evidence for some stochastic gravitational wave background from the pulsar timing array. Could that have a primordial origin? And if so, could it be linked to large density fluctuations giving rise to primordial black holes? There's rich phenomenology there. In particular, I've said there's interest in these models of inflation with sudden transitions, which kick the evolution out of slow roll into this ultra slow roll phase. And there we need to sort of consider these non-adiabatic effects. That on small scales, that corresponds to particle production on sub-Hubble scales, but on super-Hubble scales, that can leads to the study of non-adiabatic perturbations during inflation. And they can enhance the density perturbations on large scales. And could give interesting phenomenology. But to model extreme events like primordial black holes, we really want to develop a sort of non-perturbative description of these fluctuations. And that's where we look to the large scale limit to be able to follow the non-linear evolution on these scales. So that's work in progress, and I hope I've given some idea of the work that we've been doing recently. And I'll finish with that, and just a picture to show that although I'm not with you, we were lucky to have Giovanni with us in Portsmouth this summer. So it's been nice to talk again remotely and tell you something about my work. So I'll stop there, and if people have questions, I'm happy to try and answer them.
Thank you very much, Professor. Very nice picture. I remember it was very nice, my stay there in Portsmouth. And also, thank you very much for accepting our invitation, no, to us. And then now someone has a question for the professor.
Can you hear me back, Professor?
Yes, yes.
Yeah, I have a question. If you're thinking two-field inflation, for instance, you have the sub-Hubble evolution of curvature perturbations is the trajectory of the inflatonous curve, right? So in that case, the adiabatic regime or the adiabatic limit is reaches, for instance, during reheating when the non-adiabatic perturbation may decay. In the case of single-field inflation during ultra-slow roll, how is there a mechanism to reach the adiabatic limit?
Yes. So in fact, it's probably more direct in multiple field inflation. So thank you. Yes, I talked about non-adiabatic effects in single field inflation, but a natural way to produce to allow for relative fluctuations, non-adiabatic fluctuations in the phase spaces to have a higher dimensional phase space because you've got more than one field. And in that sense, that case, of course, if the more than one field survives as a light field until the end of inflation, you have to even consider the effects through reheating, as you say. But in a single field case, these ultra slow roll phases tend to be transient. And so they tend to evolve back towards an attractor solution, usually slow roll, or technically it may not be a very slow roll. So it might be what people call constant roll solutions. So typically you end up back in an attractor solution before the end of inflation. Only if ultra slow roll is kind of very close to the end of inflation would you still have non-adiabatic effects in reheating. So it's possible, but it's actually only if the ultra slow roll phase is very late. And if it's very late, that would presumably correspond to small scales, fluctuations being produced on very small scales during inflation. And if the scales get too small, that it's very hard to get direct information about them. So for example, if we're looking at secondary gravitational waves, you'd be interested in studying those with experiments like LISA, which is looking at wavelengths which are, what is that? It's millions of miles or something in wavelength. There are people who are looking for gravitational waves with sort of very ultra high frequency, sort of small scale meter wavelength kind of gravitational waves that could be produced in the early universe. But that's technology in development. But that's the sort of thing you might be looking for if you were looking at non-adiabatic fluctuations right at the end of inflation, producing gravitational waves, for example.
Thank you.
Thank you. Any other questions?
Thank you. Very nice talk. I have a question. These fellows in the string theory are proposing this Swampland criterion that they say that the potential of scalar field cannot be so flat as in your figure, one of your figures, right? Do you have any? You think these guys are crazy, or you think? Well, whatever you think, you tell me.
I'm not going to suggest they're crazy, but I think so. I'm interested in that connection between inflation and observations. And observations are, for example, that the large scale structure is close to scale invariant, and So the simple models we have for the large scale structure, seen in the CMB are these yes, they're very flat models in the sense that you're talking about. But they, if they work for observations, then that might be a problem for string theory rather than the other way around, I think is my, so.
Yes, I agree with you. Yeah.
I think and the other side to it is, of course, the late time observations also show acceleration. Now, there's less detailed information about the rate of acceleration and the rate of change of the acceleration, perhaps today. But again, as far as we can see, it's not changing dramatically. That would, it could be that present day observations could also be in tension with the sort of swampland conjecture. But yeah, of course, it is a challenge to derive, to see if we could derive inflation from a more fundamental theory. I obviously wasn't doing that today. I was looking at the phenomenology of simple models, but I certainly wasn't giving a string theory fundamental origin for them. So obviously there is work to be done there.
Oh, thank you.
Thank you. Other question?
Hello, Professor. Thank you for your presentation. First of all, maybe quite a dumb question. How does second-order gravitational waves generate a stochastic gravitational background?
Yes, so it's, it's just the inevitable process, really, if you've got inhomogeneities in the energy momentum in the universe. They will, so gravitational disturbances like that generate gravitational waves. If you're used to studying, so in cosmology, people have tended to study the linear limit, where you can separate the density, the propagation of density fluctuations, pressure waves, because they have this scalar, they're a scalar quantity, whereas gravitational waves are this tensor perturbation of the metric. So at linear order, they propagate independently. So the free pressure waves propagate independently of gravitational waves. And indeed, gravitational wave interactions are small. But as soon as you go into the nonlinear theory, then you begin coupling the density waves with the gravitational waves. So if your density pressure waves become large, they just at second order they have they become a source for the tensor modes.
Okay, thank you.
Yeah.
Well, and another question is, I heard about the probable discovery of stochastic background gravitational radiation, and I was wondering how could you distinguish between how do you say inflation generated gravitational waves from a phenomena that happened after inflation?
Yeah, so that's right. So one should realize there are other sources of stochastic gravitational waves, and for pulsar timing, there's a natural source in terms of mergers of even supermassive black holes, astrophysical, but supermassive black holes in the late universe. And so you need to, so you need more information than we have currently, I think. Although so the first thing you do is you detect there is a signal with some amplitude, and I think the next thing, which they're already trying to do, is constrain the spectral index, the scale dependence of that. And so these models, I didn't have a figure or even a sketch of this, but where are we? So let's go back to my slides here. But basically, you're looking for a characteristic shape for that. And although all I've shown here is a cartoon of the scalar power spectrum, nonetheless, the gravitational waves reflect, if you have a very strongly peaked scalar power spectrum, then it's somewhat smoothed out in the gravitational waves, but you would again look for the rise and fall of the power spectrum of the gravitational waves. And yeah, and there are some sort of general predictions, as I've shown here. In fact, the scalar power spectrum rises as k to the fourth. I think the gravitational wave power spectrum corresponding to this rises something like k squared, if I remember correctly. So there are, yeah, you look at the power spectrum in the first instance.
Okay, thank you.
Hello, Professor. Thank you for your nice talk. I have two questions. First, there was a plot in one of your slides in which where the fluctuations were like parallel with each other, and that's where you talk about the difference between adiabatic and non-adiabatic perturbations.
Yeah.
So my first question is if you could explain again the difference, please.
Yeah. So yeah, so this is kind of how adiabatic and non-adiabatic gets used in cosmological perturbation theory. Really, when you're looking at the origin of structure in the universe, the successful standard model is based on this particular type of initial perturbation, the adiabatic perturbation, and and as I say, these are like I think they're called adiabatic. One way to understand it is if you remember the usual Friedmann-Robertson-Walker universe has an adiabatic expansion. So the density, for example, changes as the universe expands without exchanging heat with any external bodies, of course, because it's the whole universe. And so this, in fact, here it's the solid black trajectory in phase space. That's the evolution of the homogeneous and isotropic, background universe. So in a sense, anything along this line is an adiabatic, so the evolution in the phase space is the usual adiabatic expansion of our universe. So adiabatic perturbations are precisely fluctuations that maintain, that are fluctuations along that background trajectory. So you disturb the density of photons and radiation, but so photons and baryons, for example. But you do it in such a way that actually it's just like advancing, expanding a bit of the universe a bit more or a bit less compared to the standard evolution. So delta rho over rho dot is equal to delta p over p dot. It's just like a time fluctuation, delta t, backwards or forwards along this evolution. And the curvature perturbation is just that turned into a dimensionless expansion. So it's h times this fluctuation in time along the background trajectory. And if you're on the background trajectory, basically everything has the same time fluctuation. So delta rho over rho dot is equal to delta p over p dot. For example, it might not immediately be obvious from that, but this relation also implies that the photon to baryon ratio, for example, is also maintained. You just expand, you maintain the baryon and photon number as you expand or compress different regions of the universe. So that's what we mean by adiabatic. And so non-adiabatic is anything which disrupts that behavior, where you introduce a fluctuation in the photon to baryon number, and that means that the fluctuations map you onto a different trajectory in the phase space. Does that help?
Yeah, it helped me a lot. Thank you. And my second question, maybe a little too technical. I think I saw two terms in one of your equation. I don't remember what equation, but it was an alpha k and beta k. Were those Bogoliubov coefficients or
yes,
not?
yes, indeed. Yeah, thank you. Yeah, I rushed over, I suppose, that, but yeah, just to show in these kind of in the very simple slow roll, ultra slow roll models. Yes, this mode, that's right. So alpha and beta here are Bogoliubov coefficients corresponding to, so U is a rescaling of the curvature or equivalently the scalar field fluctuation. And so if you write it in this Mukhanov-Sasaki variable U, it has this simple mode equation. So for slow roll, in the simple slow roll or ultra slow roll limit, this evolution of Z, or in particular the time derivatives of Z, give you a very simple solution here. It's basically so these correspond to basically fluctuations of a free field in de Sitter. And yeah, there's the positive and negative frequency modes of the quantum, what's actually a quantum field. And yeah, so if you start in the Bunch-Davies vacuum, alpha and beta are 1 and 0, but the transition, if you look at and then at the transition, you can kind of map those direct onto a sudden transition from slow roll to ultra slow roll just introduces a change in the Bogoliubov coefficients. So usually in inflation, once you've set alpha equal to 1 and beta equal to 0 at early times, you evolve that forward into the large scale limit. But now with these sudden transitions, you have a Bogoliubov transformation. This is, in fact, this actually goes back to a paper of Starobinsky's in the 1990s, where he studied these sort of sudden transitions. But so the paper with Joe Jackson last year goes into this in detail.
Yeah, thank you. I look forward to read your paper.
Yeah, thank you.
Questions? Professor, is possible to the separated universe approach be consistent with an evolution of the common curvature perturbation on superhorizon scales?
Well, only in the presence of non-adiabatic fluctuations. So I'm not sure what the best slide is to show that necessarily. I mean, so for example, for a single scalar field, I think somewhere, yeah, I have this very general result. But this is, of course, for a single scalar field in general relativity. So you have this simple result that the time derivative of the curvature perturbation is directly related to the non-adiabatic nature of the perturbations. So if you have a slow roll solution in particular, that means that in the large scale limit, I should have said this, basically this attractor only it exists in the large scale limit, so that forces the non-adiabatic pressure to be 0, and so R is a constant. Where are we? But more generally, you can have time evolution of R even for a single scalar field and in general relativity, but it has to be due to some non-adiabatic. You can relate this to the non-adiabatic pressure perturbation, this time-dependent term here. So time evolution of the co-moving curvature perturbation to me implies that there's you don't just have a one-dimensional phase space. You've for some reason got a two-dimensional phase space, such as in ultra slow roll. Yeah.
Okay, thank you, Professor. Thank you very much. Okay.
Thank you.
Next speaker. Juan Zarate.
Hi, Giovanni, can you hear me?
Hola, hello, Juan.
Can you hear me?
Yes, we can. Can you
Okay,
check
okay.
we have your slides, please? No me, hello, can you hear me?
Can you see my screen?
Can you hear me?
Yes, yes.
Yes.
Can you see my screen?
Yes, we can.
Okay. I'm going to turn off my video because my internet is a little unstable, okay? Well, my name is Juan Zarate Pretel. I am a postdoc at CDPF in Brazil. And in this opportunity, I'm going to talk about dark energy effects on neutron stars. This work, it was in collaboration with Mariana Dutra from ITA, São Paulo, and Sergio Duarte from CDPF. So, I will start by giving a brief summary of dark energy models, and then I'm going to talk about compact stars in general relativity. And the basic question in here is, what is the universe made of? According to the latest data sets coming from cosmic microwave background radiation and type 1a supernova surveys, we know that approximately 4% is ordinary matter, 20% is dark matter, and 76% is dark energy. And in this work,
Sorry, Juan, can you remove this advertisement, please?
can you hear me?
¿Cómo? The slides is not changing, please.
Not changing.
No.
Here is changing.
It's freeze. One
moment.
But is here or is there?
Here is changing my screen, my slides.
Disculpe. Okay. Okay. Yes, now it's working. Thank you.
It's changing?
Yes.
Okay, continue with the presentation. And different energy models have been proposing to explain the mechanisms that lead to dark cosmic accelerations, such as vacuum energy predicted by quantum field theory, extra dimensions, quiescence models, modified gravity theories, and isotope fluid with large negative pressure, known as Chaplin guys. And in this work, I specifically talk about Chaplin guys. Why this gas? Well, as a potential candidate for the late time acceleration expansion of the universe, the Chaplin guys and its generalized models have significant implications to modern cosmology. And the original form of the Chaplin guys is given by equation 1, P equal to minus B over rho, where P represents the energy density, the pressure and energy density respectively. And here P is a positive constant. And such a gas has some remarkable characteristics, such as it provides a plausible solution for the unification of two uncharted components, dark matter and dark energy. it behaves like a cosmological constant at late stage and does matter at early stage. And it can be obtained from the string Hamiltonian action for the branes. And there is also a generalized Chaplin guise given by equation of states, where a new parameter alpha appears. And such a model has been confronted with different observations. For more detail, you can see this reference. And the most general score is given by this equation in yellow, where the 3 degrees of freedom A and alpha have been measured by different observational data. Well, if we assume that the dark energy is an exotic fluid responsible for the selective expansion of the universe, then dark energy must be present in any region of space-time, including spherically symmetric objects such as compact stars. And in the last few years, the effect of dark energy described by a Chaplin-type equation of states on the relativistic structure of single compact stars have been investigated. For example, see this reference. And it has been shown that the Tolman-Oppenheimer-Birkhoff equation provides maximum masses above 2 solar masses, which favors the observational measurements. And these dark energy stellar configurations for a mass radius diagram similar to that of quark obey the causality condition, and they are dynamically stable under radial perturbations. So, motivated by this study, we will extend this investigation of single-phase compact stars to a hybrid scenario, but considering dark energy as described by the modified Chaplin guise. Therefore, in this work, we investigate effects of dark energy on the internal structure of an neutron star composed of 2 phases, which leads us to wonder, do stable neutron stars have a dark energy core? So we consider a core of dark energy and a crush of ordinary matter. And we investigate if such stars are stable or unstable with respect to small radial perturbations. And given a spherical symmetric line element by equation 2 and an energy momentum tensor given by equation 3, which describes an isotropic perfect fluid, through the Einstein field equations we obtain the well-known Toff equations, that is equation 4, 5, and 6. This equation describes the hydrostatic equilibrium of a compact stars in general relativity. So we have M, P, ρ, and C, 4 variables to determine in the solution of these equations. But given an equation of state that is P as a function of ρ, we only have 3 variables. So we need 3 boundary conditions given by equation 7, where rho c is the central energy density of the star, and m is the mass function throughout the star, and this condition comes from the Schwarzschild solution outside the star. And here we determine the radius of the star when the pressure goes to 0 or drops to 0. And the total gravitational mass is denoted by the letter capital M. And since we are interested in investigating the stability of these hybrid stars, we have to use the equations already known for the homogeneous case, which were derived by Chandrasekhar for the first time, where gamma denotes the adiabatic index, delta p here is the Lagrangian perturbation of the pressure, and these 2 equations have the boundary conditions 10 and 11. this condition at the center of the star and this condition at the surface. But in this study, we are dealing with phase transitions. There is two phases for the star. So it will be necessary to use appropriate junction conditions of the discontinuous phase. And here we use the junction conditions established by Pereira. You can see this reference for more detail, which describes the phase transitions according to the velocity of the phase transition near the discontinuous phase. And basically, we consider a compact star of the following form. A dark energy core in this orange sphere, described by the Chaplin guys, from the center to the radius of the discontinuous phase. And a cross, described by ordinary matter, here in science, in science color. And for that, we use the polytropic equation of state, where RDs is a radius of the discontinuous phase. That is, where the pressure corresponds to the energy density discontinuity. And that radial coordinate, we can obtain an explicit expression for the Chaplin parameter B, that is equation 13, where rho d minus is less than rho d plus. And we define a new parameter alpha by this expression, where rho d minus is the energy density where the crush begins, and rho d plus is the energy density where the chord ends. And therefore, our toy model is described by 6 free parameters: rho c, rho d plus, alpha, eta, kappa, and a. And for these specific values, we have this equation of state. The orange lines correspond to the core, and the blue line corresponds to the crust of the star. And here we have some numerical solutions for a specific central energy density. For example, 1.5 times 10 to 15 grams per cubic centimeter. Here we have considered alpha 0.9, of this plus 0.8. And we observe that both the density and pressure are decreasing functions with a radial coordinate. Meanwhile, the mass is an increasing function as we approach to the surface. In addition, we can see that the pressure and the total gravitational mass increases as A becomes larger. And for this construction, and in the next figure, we have adopted eta equal to 1 and kappa equal to 100 square kilometers. We have adopted these values because they describe typical neutron stars. But this plot is obtained only for one central energy density. When we vary the energy density, we obtain the well-known mass radius relation of compact stars. And here, the numbers associated with each color indicate the different values of alpha, where we have considered rho d plus equal to 0.8 times 10 to 15 grams per cube centimeter. And we observe that if we keep alpha fixed and vary alpha A, for example, the black lines, you see that the mass undergoes a substantial increase as A increases. And if we consider a fixed value of A, for example, here the solid lines, we observe that the gravitational mass decreases as alpha gets smaller. And remarkably, for alpha 0.4 and 0.6, there would be unstable stellar configurations in the low central energy region, because here the derivative of n with respect to rho c is negative. And here we can see better the behavior of the mass maximum in terms of alpha and on the critical central energy density. The critical central energy density corresponds to the maximum mass configuration here. Okay? So we see that an increase in alpha leads to an increase in value of the maximum mass, but a decreasing value of the critical central energy density. And on the right plot, we show the radius of the discontinuous surface and the radius of the stars as functions of the central energy density. And we observe that with a fixed value of A, for example, like here, the solid lines, the radius of the core or of the discontinuous surface decreases as alpha becomes smaller. But the behavior of the radius of the star is less trivial. And here we present the square frequency of the fundamental modes for a specific value of the inner energy density. We have the square frequency as a function of the central energy density and as a function of the gravitational mass. And we see that slow phase transitions produce larger frequencies than rapid phase transitions. Know that solid lines here denotes slow transitions, and dashed lines represent rapid transitions. The upper panel represents are the results for alpha 0.8, and the lower panel represents the square frequency for alpha 0.4. In addition, we can see that the radial stability of the star increases as A becomes smaller, in the sense that the central energy density, where the square frequency vanishes, increasing. And on the right plot, we show the square frequency as a function of the gravitational mass. And we see that the maximum mass point corresponds to the transition from stable compact stars to unstable compact stars. So the maximum mass point can be seen used to a turning point from stability to instability. And another interesting characteristic of this study is that here we can see some stable stellar configurations. This is because in these plots there are two regions of unstable stars, here on the left and here on the right. But we observe that only rapid phase transitions can describe unstable configurations at low energy densities. Well, we were also interested in comparing our results with different observations, so we choose two values for Rodis plus. The black lines represents Rodis plus for 0.5, and the blue lines correspond to Rodis plus 0.8. Here is a mass radius relations, and the different bands here, for example, orange, cyan, correspond to the Milky Way, correspond to the fastest spinning neutron star in the disk of the Milky Way. And the orange bands correspond to the secondary companion detected by the gravitational wave signal given by this. In addition, the magenta, brown, and red dots with their respective irregular bars represent the masses of the millisecond pulsars given here. And in this plot, we present the oscillation spectrum under the effect of rapid phase transitions, and we see that the stellar configurations presented here are stable under small radial perturbations until the maximum mass. And finally, we were also interested in considering more realistic equation of state to describe the crust. So here we use the slide 4 equation of state, which is based on the effective nucleon-nucleon interaction. And we obtain similar results to the polytropic equation of state to the crash. In fact, similar to the polytropic case, given a central density rho c, the gravitational mass of the hybrid stars increases with both A and alpha increasing. And on the right plot, we show the tidal deformability as a function of the gravitational mass, where the magenta vertical line represents the observation reported by LIGO-Virgo collaboration by analyzing the tidal effects of this event. So, in conclusion, in this work we have shown that it's possible to the existence of neutron stars with a dark energy core because they are dynamically stable under small radial perturbations and because they are compatible with the recent astrophysical measurements. And for more details, you can see my recent article published in this reference. And that was.
Thank you, Juan. Any question? No. So, Juan, can you hear me?
Yeah, yes.
Okay, great. So you split the star in a Chaplygin core and a polytropic crust outside. So how can you define this transition point? I didn't get this information. Is it a free parameter and then you should fit it? Can you give some words on that?
The alpha parameter measures the jump in the dark energy, in the energy density at the transition. Here, for example, alpha. And the smaller alpha indicates a large jump in the transition.
Okay. Thanks.
Yeah, I have a question. Actually, you are using the chaplains in gas for the interior of the star. But why you are calling that dark energy? I mean, I agree that this is a peculiar fluid with a different equation of state, and then you have this transition. But why you are calling it dark energy? If it's dark energy, it could be present everywhere.
Yeah, interesting questions. As a toy model, we consider that the dark energy is confined only in the core of the star, but actually we are investigating the dark energy in all the star, mixed with ordinary matter. But this work was only a toy model. For future study, I will consider more general cases.
So outside of the star, is there dark energy?
Yeah. But with ordinary matter, in addition to dark energy.
Okay, thank you.
Other question? Yes. Thank you very much, Juan.
Thanks.
Next speaker is Diego Molina from University of Arturo Prat. Good. Yes.
Hello. Okay. Well, first of all, thank you for the organizers to invite me to take the opportunity. I can take the opportunity to be here today with you, and thank you so much. First of all, the title is different from the schedule. Sorry for that. That is my fault. For don't send the abstract on time. This talk is about two works that have been working on these last years. They start in 2017 and go on with two, maybe three works that we are working on. All right. The motivation, and that is what I try to do, is convince you that this is important. Okay, the Maxwell algebra is important in this work. Maxwell algebra you can find in some early works that describe particle system in a constant electromagnetic field. So you have the Lorentz generators and the momenta, but different from Poincaré, the P con P is follows to zeta, that is a generator for the electromagnetic fields. And in many other cases, this algebra can be found in different contexts, not explicitly in electromagnetic fields, but you can make a gauging, just you can gauge to obtain general relativity, you can change this symmetry to obtain action with different contribution of matter fields and whatever. In cosmological models, I know that this many people working also under this kind of symmetry, and in many contexts that I don't follow so well, but I know that they do. Also, there are several symmetric and higher spin extensions of the Maxwell algebra that have been formulated with many authors, so there's a lot of interest in this. But we are focusing the 3 dimensions, 2 + 1 dimensions. When it is possible to define a Chern-Simons gravity theory that is very useful for us and many contexts. And how can we do that? Okay, these are the same algebra dualized for the index. And this guy over here is the bilinear invariant form that is what you need to construct the Chern-Simons action. So we have a Chern-Simons gravity theory under this symmetry. We can make the connection that with the fields that are duals to the generators and make the curvature. And with all this stuff, we put this in there and in a Chern-Simons form, and we get this Chern-Simons Maxwell Lagrangian action invariant under this symmetry. So the explicit form of this Lagrangian is this. You can recognize the Einstein-Hilbert, the Chern-Simons over the connection spin and more fields. You can find a lot of interesting application of this, like the infinite dimensional asymptotic symmetry, that is something on the research that made for the 3 dimension for these people. Making a dimensional reduction follows in a 2-dimensional action, that is get you the Hawking case about gravity. You can study the non-relativistic limit, like the Carolian limit, the ultra-relativistic, right? And a kind of Galilean limit, non-relativistic both. So, more than that, the supersymmetric, hypersymmetric, higher speed extension, a lot of kind of stuff that my colleagues and I we are working in the last years. And maybe the most fun of that is an effective model of a topological insulator by Palumbo, sorry. That is, for me, is really interesting. He used a Chern-Simons in 3 dimensions to do something in that topic. All right, so the outline, if I can convince you that this was fun, is explain to you a little technique that the infinite semigroup expansions call is about how can you take a Lie algebra and make another one, all right? This is a simple mathematical tool. We work on that in an example to see what happened with Poincaré and the non-relativistic expansion of Poincaré and how this can be reproduced with this infinite expansion procedure. And that is useful for us to understand what is going on here, that is an expansion of ADS using the cosmological constant. And I will try to convince you that Maxwell symmetry is between the Poincaré symmetry and the ADS symmetry, all right? So we recommend Maxwellian gravity, and we can talk about the discussion and stuff. All right, so Lie algebra expansion allows to relate, like I said, 2 different Lie algebra using an arbitrary Lie algebra G, that is the commutator of generators, the constant structure, and an abelian semigroup S, that is 2 elements that multiplies and give you another elements, of course, with a K selector that gives you the rule of multiplication. So if you take the algebra with the semigroup, you get another algebra. That is a little boring because it's like many copies of this, but it's different, okay? It's a new algebra. So these new generators are the Cartesian product, more or less, of the element of the semigroup and the old generator. And the new structure constant is the other one with the K selector. So it's a more bigger in one sense, Lie algebra. Then we can use the reduced expansion that is considered inside the semigroup a 0 element. So it's not like that, but it's like a multiplied by 0. So these 0 elements eliminate some generators, some part of the algebra. So this, even more, it can reproduce the Inonu-Wigner contraction. And even more, you can make a resonant expansion, that is, you take the algebra and the sum of subspaces and discriminate V0, V1, Vn, and you make the same with the semigroup. And just like this, if they have the same structure, if the vector spaces has the structure similar to the semigroup, you can make some resonant algebra, follow the chord of a piano when you put some chord to follow the resonance between the notes. Right? So the new algebra is the multiplication about with the V0 with A0, V1 with S1, and so on. And this is still a Lie algebra. So, but this is not a sub-algebra, it's not inside, it's another one. That is the funny thing. So one example is take the non-relativistic expansion of Poincaré algebra, that is the rotations and the momentum. These are the only commutations that are different from 0. And you splitting the indices in this form. You take the temporal generator and the space generators and discriminate between the 2. Then you put a little parameter and send these parameters to infinity, or to 0, sorry. And this is representing a Inonu-Wigner contraction, and you close into the Galilean algebra, right? This is a different algebra, the same dimension with a Inonu-Wigner construction. But this procedure, known as Inonu-Wigner, can be generalized considering the Lie expansion that I was talking about. We repeat the process from this point of view. We have the Poincaré algebra. We put these 2 sets of generators, V0 and V1. We see that they have the zeta-DOS structure. And we choose this semigroup with this rule of multiplication that has a 0 element and make the resonant, right? We separate the set of semigroup in two sets, right? And we can see that follow this structure that is the same of the sub vector spaces of the algebra. We take the resonant, we take away the 0 element, and we arrive to a reduced algebra. I don't choose the particular semigroup in this case, but if I take the set with 3 elements, I can make the same procedure. I can rename the generators in this way, and I can get the Galilean algebra. Because my semigroup, I chose well my semigroup. That is the thing. So this is now an infinite speed of light limit of the Poincare symmetry. This is the parameter, right? I take the velocity of light to infinity, and I get Galilean algebra. But if my semigroup is a little bigger, so I get the extended Bergman algebra. I have 2 more generators, and this is a new algebra with the same procedure. So further extension introduce more generators, and if the semigroup is bigger, I get bigger algebra. The SE3 can be used to define an action even for a gravity Newton-Cartan. So the idea is, all right, take an infinity group, all the elements that you can get. So particular cases will be a different kind of algebras. And we take this kind of element of the semigroup to this set of generators, and the other one to the other generators. And this is a generalized Poincare, Galilean algebra, infinite Galilean algebra that is an infinite algebra with these commutators. So we can see that every element of the semigroup, lambda, is related to the parameter of velocity of light, because we know that if we take the parameters to infinity, we get some Galilean algebra, or some kind of, right, non-relativistic algebra. So this element of the semigroup have to be related with this physical parameter. So the idea what is consider an one-form connection that takes value in this infinite algebra. So this is the connection, these are the generators, and these guys, these field guys, can be write as powers of the speed of light in multiplication with these infinity generators, right? It's an infinite series of sums. So this is a non-relativistic expansion of the gravitational fields that allow us to construct the post-Newtonian expansion of general relativity and Chern-Simons action. So the idea, this is the principal idea. I can write the fields like an infinite sum of another fields in powers to velocity of light. But the velocity of light is related to the elements of the semigroup. So can we make the same with the cosmological constant? But in this time, we take the ADS algebra and make the same. In this time, we have J and J, that the rotation means the rotation that is close, the rotation with the momenta that is false in momenta, and P con P is J. So as before, we introduce a parameter sigma, and we rescale the generators, we put sigma to 0, and we get the Poincare algebra. So it's the same phenomenon. Now sigma is related not to the velocity of light, is related to the cosmological constant, or the ADS radius. And so we take the suspension procedure from this point of view. The V0 element is the rotation, and the V1 is the momentum. Or, of course, again, satisfy the set at 2 graded structure. We take the same semigroup, and we make the resonant and reduced algebra. We make the multiplication of the elements with the generators. And we get some cases, again, with a little semigroup reproduce the inordinate contraction to Poincare. So with this SE1 semigroup multiplication with the ADS, we fall into Poincare algebra. if we take SE2, sorry, there's a little more generators in 3 dimensions, we get Maxwell algebra from the ADS, right? And the idea is now take the same as before. We take an infinite number of elements for the semigroup and multiply the generator of the ADS. And we get this. It's an infinite Poincare because it's an infinite extension of the algebra of Poincare. And now, these generators that are infinite and the fields associated are also infinite. So we have to make a truncation. This algebra in particular has been used for curvature correction to particle models on Minkowski space. And just like above, we take an element of the semigroup associated with a power of L. And the connection is right as an infinite sum of fields and generators. And this reproduces me a generalized Poincare algebra that is infinite. So if I can cut the series in some point, I can get whatever I want. In the case of mega Chern-Simon action, I write the same action, the Chern-Simon action. I put this connection with this in bilinear invariant form with the constant here. We dualize. The most simple case of the series is take only the first one, the one order. And I have to rescale also this constant that come from the topological invariant. If I do that, I get the Chern-Simon action for the composed with the Chern-Simon action for a spin connection, the Chern-Simon Maxwell, and I don't consider the superior order in R. So what I get is this guy. So this is very useful in many theories. This can recognize the Einstein-Hilbert, the Chern-Simon for connection spin, and more fields. So this procedure can be generalized to cut the series in wherever I want. That is the idea. And the resulting Chern-Simon action will be invariant under generalized Poincare algebras. And this provides a systematic way to add L correction to gravitational theories, obtaining from gauging the Poincare symmetry. I take the Poincare symmetry to infinite, when it's gauging, and then I cut the series where I want. I can fall in Poincare again, or Maxwell, or more. So this is an example. It's in 4 dimensions also. I can take the McDowell-Mansouri action, and I write the curvature. I take up to the order of L/2, the cosmological constant. So I cut the series and introduce a new constant to make all good works together well. And we find the Maxwellian gravity action, that is Einstein-Hilbert action, the contribution, of course, of this order of Maxwell, and I don't consider the rest of the series. So this can be used systematically to go and go on. So maybe I go too fast. I'm sorry. The infinite algebra expansion with the infinite semigroup can apply to physical systems and reproduce things with a physical parameter, the velocity of light, the cosmological constant, and maybe more. I don't know. The procedure of adding 1/c post-Galilean or post-Minkowskian correction to non-relativistic gravity is captured by this procedure. I can reproduce that it is known, but the thing is that maybe we can be on. The results can be generalized to the case of expansion in powers of the cosmological constant. I don't just make this to the velocity of light, also in the cosmological constant. Maxwellian gravity in 3 and 4 dimensions can be obtained as the subleading term in the cosmological constant expansion on ADS gravity. That is the reason because I said that between Poincare and ADS is Maxwell, because if you want to write ADS, you have to write every single term of the infinite series. But if you cut the series, you fall between the two algebras. There are two work in process from this point of view. The first one is the computation of the asymptotic symmetries of the Chern-Simons invariant under a generalized Poincare algebra. With this based in this work is similar to this work when they do the same work with the velocity of light. And the other work in process is the computation of the one-loop partition function of the Maxwell invariant Chern-Simons gravity, based on the two very known resolved in the context of ADS and Poincare cases that they have asymptotical flat solution. So Maxwell has two. So this is another road that I can get. Thank you so much. Yeah, we're focusing 2 plus 1 direction, yeah. Your action is freeform. Yeah. I put an example of 4 dimension because it's work well too, but the focus is in 3 dimension, yeah.
No, but the second term is a 4 form.
Oh,
yeah, this is a type.
That is a mistake, yeah, I'm so sorry.
Yeah. Appear to
Yeah, it is.
There is playing a role the torsion in some place?
Oh, okay. There are some works with Patrick Emelin that generalize the cosmological content on the Maxwell symmetry, and I can't remember now. But yeah, I mean, in 3 dimensions, no. In 5 dimensions, I think yeah. You have to consider the torsion as well. That is a good reason to work in 3 dimensions.
Okay. Thank you.
Okay.
Thank you. Other question?
Thank you. Great presentation, and I love the last slide.
Yeah. Always happen.
What is a topological insulator?
Oh yeah, that's a very nice question. I mean, I read the paper, it's not my topic, but Palumbo, used the Chern-Simons action in 3 dimensions, invariant under Maxwell symmetry, to build something that reproduces a topological insulator. That is not my field, but if I remember well, there are 2 potentials that don't touch, so that insulator is between the, so you can use it like a superconductor, I think. This gap that happens in this material. So this is the more applied thing that I found in this. Yeah.
Okay.
It's not poetry.
If you allow me another question, could you explain a bit more about truncating the series, and if you leave the series complete, then you have all symmetries of ADS.
Yeah.
And if you truncate it, then you obtain
you get Poincare, Maxwell, or maybe a B algebra that is called more generators, infinity generators. If you cut the series, if you don't cut the series, you get ADS.
Okay, very interesting. Thank you.
Thank you. Thank you. Yes. More questions? Okay. Thank you very much, Diego.
Thank you.
Now we have the picture of the event, please. Then we go there.